Hello, Physics Nation. My name is Nate Larmond, and I'd like to do a Khan Academy problem from a set called Equilibrium and Applied Force. So equilibrium is a state of balance. I am in equilibrium right now. Gravity pulls me down, the chair pushes up. That's called the normal force. And if you add those two forces, you get nothing. I am not accelerating up, down, left, right. That's called translation. If your angular orientation remains the same, but you shift up, down, left, right, that's called translation. So if the sum of the forces is zero, you have no translational acceleration. If the sum of the torques is zero, you have no angular acceleration. All right, so here's translation, here's angular displacement. And those are the two conditions for equilibrium, they're called. The sum of the forces have to be zero, and the sum of the torques have to be zero. So let's read this problem. A uniform meter stick with equally spaced tick marks has a fulcrum at its center, and the downward force F is applied to the meter stick at the position shown. Another downwards force, 3F divided by 2, is then applied to the meter stick. At what position should the downward force, 3F divided by 2, be applied to keep the meter stick in equilibrium? Okay, so our test typically has two parts, multiple choice and free response. You don't have to justify anything. So for the multiple choice portion, there's no like choose a formula, write the sketch, show me all your algebra. There's no justification. There's no explanation. You just get the right answer. So I'm going to try that first. So here's the second force. Here's the pivot. The second force is 50% greater. 3F divided by 2 is just a fancy way to say 1.5 times this force. So how far is this force from the pivot, from the fulcrum? Well, it's 1, 2, 3 of these little units. In my sample calculation, I split the left into 1 unit and the right into 1 unit. So that was kind of stupid. I called this 0.2 and this 0.4, 0.6, 0.8, 1. But it's probably just easier to say 1D, 2D, 3D, or 1R, 2R, 3R. Anyway, it's 3 of these little distance units from the pivot, the axis of rotation, the fulcrum right here. And this force is causing, let's see, a counterclockwise torque. And in math land, that is positive. Okay, so let's do the right-hand rule for counterclockwise. That's going to send your thumb at you. That's the positive Z rotation. So we can eliminate two ridiculous choices. If you put a second force on the left-hand side of the meter stick over here in x1 or x2, it's going to cause another counterclockwise torque, right? So that can't balance out. You can't add two counterclockwise torques and get zero. That means our second force has to be on the right-hand side. So if it was the same force, right, we know it would have to be at the same distance, 1, 2, 3 little distance increments from the fulcrum. But it's not. It's 50% greater. So that's the little puzzle. Does a bigger force applied at, let's see, 1/3 of this distance? This is R1, or the original lever arm. So should this new R2 be 1/3 the original distance, or should it be 2/3 the original distance? This is R2 that I'm trying to figure out over here. And intuition won't tell you. Like, you really have to do a numerical analysis. But notice how you can eliminate two ridiculous choices. It is not on the same side as our first force. It can't cancel out a counterclockwise torque. So let's do a little numerical analysis. Where is my work? Whoops. Pardon the scrolling. Okay, so like I said, my sketch was kind of unnecessarily complicated. I called the fulcrum the middle, and I said, well, here's our given radius. I split it up into 0.2, 0.4, 0.6. I said it was 60% of the left-hand distance. And what they want to know is, should R2 be 0.2 or should it be 0.4? Should R2 be 1/3 of this R, the original lever arm, or should it be 2/3? If you're clever at math, you can do this in your head, but we got to spell everything out. So now we're sort of in the free response portion of our standardized test. If it's multiple choice, just get the right answer. No explanation, no justification. But here, you have to grab what they call a general principle. And if there is equilibrium, that is, if there's no acceleration, you could say the sum of the forces is zero. And if there's no angular acceleration, if there's no twisting acceleration, you can say the sum of the torques equals zero. This is the traditional sign convention, like I said. Let me see, is this? This is counterclockwise for the screen, I think, because it's clockwise for me. So that should be a positive rotation for you. Did I say that right? Hang on. If the fingers wrap in the counterclockwise direction, the thumb should point towards you, out of the screen. That's the traditional sign convention from the math teachers. Counterclockwise is positive, clockwise is negative. Anyway, there are three torques acting right here. The first one is provided by the problem. They just say a force of F, and they give you the radius, three little tick marks. I called that 0.6. I called the tick marks 0.2, 0.4, 0.6, 0.8, and then 1 was the far left-hand side. Maybe stupid, maybe unnecessarily complicated, but that's what I did. Here's the unknown torque. Here's torque 2, I should say. That's F2. They say it's 1.5 multiplied by the original force, or 50% greater than the original force. And we're trying to find R2. Well, here's a third torque, except it's zero because the weight of the stick is passing through, the weight of the stick, the center of gravity of the stick is right there, and it's going right through the fulcrum. So no torque is applied. We did a lab to figure out what the weight of the stick was. Anyway, that's a previous experiment. There is no torque provided by the weight of the stick. It's not that the weight of the stick is zero, it's that the center of gravity is on the support, on the fulcrum. So there's no lever arm. There's no torque applied. So let's substitute in what we know. Here's the known force, here's the known distance, here's the known force but unknown distance. And the signs are really important. This guy is a counterclockwise torque. He is causing the meter stick to rotate this way, counterclockwise. And this guy is a negative torque. So on the right-hand side of the pivot, we're going to cause a clockwise torque. So just watch your signs, be careful. This torque is negative, this torque is positive, and this torque is zero. I'm going to add this term to both sides. And over here is full generality. It might be better to just say F1 cross R1 equals F2 cross R2. That way you can just divide both sides by F2. So, hey, look at this. The ratio of forces, F1 divided by F2 multiplied by R1 is R2. So, pre-packaging this algebraic solution is useful. But on the right-hand side, what I did was throw in my numerical assumptions. So the sort of algebraic miracle right here is F on the left, F on the right. If you divide both sides by F, it cancels out. F divided by F is 1. So that's what's going on right here. And then we have 0.6 equals 3/2 R2. Multiply both sides by 2, divide both sides by 3, or multiply by the reciprocal of this fraction, and you get 2/3 of 0.6, or 3 of their little distance units, is our new radius, where this bigger force should be applied. And that's all you need to know. 2/3 of the original lever arm is 0.4, or 2 of those little tick marks, 2 distance units to produce an opposing torque. Thanks for watching. See you in the next video.